So now Harvard and Von Neumann architecture difference. I have the diagrams here. You can see this. This is shared bus used by the CPU and the memory, and the CPU can separate program memory and separate data memory and separate paths also. So this is Harvard architecture. This is Von Neumann architecture. Now separate buses are used in the separate buses for data and instruction in Harvard architecture, and separate data memory and separate program memory. Now when it comes to the Von Neumann architecture, shared bus for instruction and data. I have both instruction and data stored in this memory, and this is the common path for both instruction and data. Now easier to pipeline. So this Harvard architecture is easier to pipeline, hence the good performance. This Von Neumann architecture difficult to pipeline and lower performance. So the cost is high because you got to use two separate memories and separate instruction path. So the cost is relatively low. So because there is only single memory and the data path. So no memory alignment problem. So if I take Harvard, so the memory need not be aligned. So memory alignment. If there is memory alignment, then you can access the memory much faster, but that restriction is not there in for the Harvard architecture. So when I say Von Neumann architecture, it requires the memory alignment. That means, say for example, memory alignment of 4 bytes. If I say you can store the memory words only at the memory word addresses which are multiples of 4. If I say memory alignment of 8 bytes, you can store the memory words only at the memory addresses which are multiples of 8 bytes. So that restriction is not there in the Harvard architecture, but memory alignment restriction is there in Von Neumann architecture. And one more important difference is that, so since the Harvard architecture uses separate program memory and separate data memory, so there are no chances for accidental correction of the program memory. So but here the risk of program memory correction is high because it's a single memory. Next, the difference between big Indian and little Indian processor or controller. Now Indian specifies the order in which the sequence of bytes are stored in the computer memory. How the bytes are stored, whether they are stored from the lower order byte or whether they are stored from the higher order byte. So based on that, there are two ordering of the bytes. One is little Indian ordering and other one is big Indian ordering. Now what happens in the little Indian ordering? Little Indian, it's called as little end. The lower order byte of the data, the lower byte of the data is stored at the lower address in the memory. So I have the example in the next slide. I'll show you. If I consider 4 byte long integer, byte 3, byte 2, byte 1 and byte 0, it's a 4 byte long integer. Now how it will be stored inside the memory? So this is the lower byte. So this lower byte occupies the lowest address. This is the higher byte, it occupies the higher address. I have the example here. Now byte 0, byte 1 and byte 2, byte 3, this is the lower byte which is occupying the lower address. This is the higher byte which is occupying the higher address. Now if I take this, I assume I have an hexadecimal value like this, a word, it's stored like this. So CD is the lower byte which is stored at the lower address, and 90 is the higher byte which is stored at the higher address. Now when I want to read this number, I got to read from here 90AB12 CD. So this is what even when you executed the programs, it was Intel uses the little Indian byte ordering. So this is the order in which the data was stored. You have executed many programs and this is what you have observed. You have the lower byte, lower order data stored at the lower address. Now big Indian, it says big end, that is the higher order byte of the data is stored at the lower address. In the little Indian, you have the lower order byte of the data stored at the lower address, but in the big Indian, you have the higher order byte of the data stored at the lowest address. If I consider the same example again, 4 byte long integer, byte 3, byte 2, byte 1 and byte 0, now it is stored. It is something like this. See here, we have the byte 0, that is the lower byte 3, which is the higher byte of the data stored at the lower address. Now I have the example now, 90. Now in this word, hexadecimal word, excuse me. Now in this hexadecimal word, 90 is the higher byte which is stored at the lower address. 90 is stored at the lower address, and the lower order byte of the data is stored at the higher address. Now this, when I want to read, I can read from the lower address itself, 90 AB12 CD, but there I got to read it from the higher address to the lower address. Yeah, that's about the big little Indian and big Indian controllers. Okay, now load, store operations and instruction pipelining. RISC processor uses instruction set is orthogonal in nature. That means it operates only on the register. It performs the data processing if the operands only on the registers. And the RISC processor are classified as a load and store architecture. RISC processor will not come under the register memory class of architecture. Only the CISC processors will come under the class of register memory architecture, but CISC processors come under the load and store architecture because the operation data processing can be done only if the data is present inside the register. And how to get the data to the register, it is possible only through the load and store instruction. This is a simple example now. Now I have an example here. Now say what I'm doing here, I'm loading the content of memory location X to the register R1, loading the content of memory location Y to the register R2. I'm adding the content. See, the operation, addition operation I'm doing now on the contents of the register which are present in register R1 and R2. Add R3 comma X comma Y I cannot write because X and Y are the memory location. Now data processing operation cannot happen directly on the memory location. They got to be loaded into the register, and then on the register you can perform the any data processing operation. Now the result goes to the register R3. Now from the register R3 I can put it back to the memory location Z. So the diagram also depicts the same. Now I have X, this is the memory. The X memory location is holding the data 00 loaded into the register R1, and Y memory location is holding the data 7F loaded into the register R2, and they are added. ALU is used for adding, and the result goes to the register R3. From R3 I am putting it back to the memory location Z. Next, the pipelining. I have said the instruction pipelining also. Now conventional program execution I'm considering here. I'm assuming decode and execution are happening in one stage and fetch in the another stage. I'm assuming only two stage pipeline here. I'm not considering three stage pipeline. It's only two stage pipelining. Fetch is one stage, decode and execution are combined together in one stage. So that is what. Now here 4 pulses, 1, 2, 3, 4. We are assuming 4 pulses make one machine cycle. In first machine cycle, you have the instruction which is present at address PC fetched, and the instruction which is present at PC minus 1 is getting executed. Two things are happening simultaneously. So PC minus 1 instruction is getting executed, and the instruction which is at PC is fetched. Now what's happening in the second machine cycle? So the instruction, this was fetched, instruction at PC was fetched. Now that is getting executed, and what fetch will do, it will go for fetching PC plus 1 instruction. What is happening in the third machine cycle? Now PC plus 1, which was fetched here, now it's executing, and fetch will go for fetching the instruction PC plus 2. I hope you understood this. Only thing is, we are assuming decode and execute are combined into one stage. Yeah. Now next is ASICS, that is application specific integrated circuit and application specific standard product. Now ASICS, as I already told, it's a microchip designed to perform a specific or a unique application. Now as I said, they are the proprietary products, so they cannot be sold in the open market. They are manufactured only for a particular customer. And one more important thing is ASICS products are profitable only if the customer is buying them in the large volume. If these products are not bought in the large volume, then they are not profitable. They are profitable only when they are bought by the particular customer in the large volumes, because they cannot be sold in the open market to other users. And one more important thing is fabrication of this manufacturing of application specific integrated circuit requires this non-refundable initial investment. So the company which is manufacturing the ASICs, application specific integrated circuits, the customer to whom these ICs are being manufactured, they have to provide a non-refundable initial investment to the company, and this investment will be used as a one-time investment which will be used by the company for the process technology and configuration expenses, and this investment we call it as non-recurring engineering charges, and it is one-time investment, and this has to be paid completely by the customers to whom this application specific integrated circuits are required. Now example, this is what I told, ADE 7760 energy meter, the integrated application specific integrated circuit which is used, which you can find inside the electricity meter which you find inside your in every home. And ASSP on the other hand, again application specific standard product, is not a proprietary product, so this can be sold in the open market, which can perform a specific or a unique application, but these are not for one particular customer. They can be sold in the open market to any customer who can use it. Now next is programmable logic device. These are again integrated circuits that contain large number of gates and flip-flops. They contain large number of OR gate plane, AND gate plane, NOT gate plane along with the flip-flops, and these OR gate and NOT gate and AND gate planes can be configured by the user to perform variety of functions and called as programmable, hence they are called as programmable logic device. I have the small picture here. So this is the input, so this is the AND plane logic, and similarly OR plane logic connected now, and these are all the switches. By switching on or switching off the circuits, you can go for getting the output for any function. Now PLDs are low cost again and the simple design tools than compared to the application specific integrated circuits. There are two types of logic devices again, programmable logic devices again. One is fixed logic devices and programmable logic device. Now what are fixed logic devices? The circuit is fixed, hence they can perform one or set of functions that cannot be changed for after manufacturing. So fixed logic devices. The other hand, the programmable logic device, they can be reconfigured to perform any function as the circuit is not fixed. Now again PLDs, there are two types, complex programmable logic devices and field programmable gate arrays. Now we will discuss first FPGAs. So they offer high amount of logic density and many features it offers and high performance. Now why we say high amount of logic density? Because it has around 8 million system gates. So inside the logic planes you'll find around 8 million system gates, and this can be reconfigurable. Example is Xilinx Vertex. Hence we say FPGA has high amount of logic density. Now as the logic density increases, the function, the number of functions which you can make FPGA to perform also increases. Now this has high amount of logic density because it provides around 8 million system gates. So 8 million system gates which I have shown here like this. Now CPLDs, they are called complex programmable logic devices. They are called complex, but they offer smaller logic density at about 10,000 gates. 10,000 gates you'll find. So example is Xilinx School Runner is the example for CPLDs. Next, advantages of programmable logic device. The first important advantage is that it offers to the customer more flexible during designing. So designing flexibility it provides, because what kind of designing flexibility? It allows the programmers to change the programming file and observe the changes because of that changing immediately. Now that is what the advantage of PLDs. So they provide more flexibility during designing. That means when you are doing designing, you can do many instantaneous changes, and immediately you can observe the output, and you can go for changing the design any number of times, until you get the accurate designing. And they don't require long time for building the prototype. What is a prototype? Prototype is basically an initial model or the basic model. Now using the PLDs, you don't require much time to build an initial prototype or the initial working model. So in very less time you can go for building the prototype. And don't require the customer to pay the NRE cost, that is non-recurring engineering cost. The initial investment what the customer used to pay, that need not be paid, because this designing using PLD is very flexible, and hence the NRE cost is also less, or majority of the time the customer don't have to pay this NRE cost. Once the device is ready, then they can go for buying the device with the manufacturing cost of the device. And PLDs can be reprogrammed even after the equipment is shipped to the customer. So the equipment that is using the programmable logic designs like CPLDs or FPGA can be programmed even after the device is given to the customer. So these are some of the important advantages of the PLDs. The first and the foremost advantage is this: flexibility in designing. Any number of times the design can be changed until you get the perfect design, and you don't have to wait for a longer period of time in order to build an initial prototype, and the customer need not pay the non-recurring engineering cost, that is the initial investment, because the design can be done by using the programmable logic designs, and the design can be changed any number of times without the additional cost. Next, the last topic of the today's session is the cards, commercially off-the-shelf components. These are the systems, so something like, now I want to buy some groceries, then I'll go to a mall, correct, right? I'll just pick the groceries which are available on the shelves. So I'll just go for picking the groceries which I require, correct, which suits my need. So and I'll put them into the basket. That's something like that. But the products which are available on the shelves and is used as is, correct? You pick them from the shelf and you're going to use them as it is without making any changes. So the cards are designed, they have this feature as is feature because they are designed in such a way that they provide easy integration and interoperability with the other existing system. You just pick the object. I have shown one example here. This is again an example of the cart product used for TCP/IP connection. Now for my embedded system, I need to provide a TCP/IP connection. What I'll need to do is I need to pick this from the market, connect this with my embedded system. Now that's all I need to do. That's all I need to do. I don't have to do any changes to my embedded system, and this knows how to interoperate with the other existing system like embedded systems here. Now what are the advantages? They are readily available in the market. Just as the groceries are readily available in the market, so even you have a few products which are readily available in the market, and they are cheaper also. Reduces the development time to a greater extent. Since I am picking from the market, the readily available components I'm using, I can reduce the development time of my embedded system. Reduce the time to market the embedded system also. When you're developing a new embedded system, since you're using the cards, readily available components inside your embedded system, so you can make your embedded system come to the market in a very less span of time. And so those were the advantages or the benefits of the of using the cards. At the same time, there are disadvantages or the drawbacks of using the cards as well. Now cards, if the manufacturer of the cards stops the production, because of the rapid changes in the technology, and this will adversely affect the commercial manufacture of the embedded system that uses these specific cards. Say for example, I was using in my embedded system this product of cards which provides me the TCP/IP connection. And if the manufacturer of this device for some reason stops the production, then it is not possible for me to use this specific code in my embedded system. That is the only disadvantage, because I was depending on the some other cards in order to produce my manufacture my embedded system. Now this will affect the production of my embedded systems, because the specific cards which I was using is stopped by the manufacturer. Now, yeah, that's the end. In the today's session, you understood the core that can be used in an embedded system. Many of the cores you understood, starting from the microprocessor, microcontroller, and then application specific integrated circuits, and or ASSP, application specific standard products, which is a non-proprietary product, whereas ASIC is a proprietary product which can be sold only to a particular customer, and they cannot be sold in the open market. Then you understood the other core, DSP, digital signal processors, which are used in the embedded systems that are specially designed to deal with the multimedia data. And then you understood the programmable logic devices, two programmable logic devices which can also be used as a core in the embedded system, that is complex programmable logic device, and other one is the field programmable gate arrays. With this we completed chapter 2 in the module 3. In the next class, we are going to discuss the other chapter from the module 3, which mainly focuses on the sensors and the actuators. Now, we'll end the today's session. Thank you, dear students. Just be at home and protect yourselves from the COVID-19. Thank you.